All right. Everyone's at the typing in phase, which is good. Just use that less than symbol or greater than symbol to denote kind of the edges of your vector. Afternoon. You keep saying what?
You're not, you didn't respond after you pressed submit.
Submitting for me. Okay, then just don't put them in there. Didn't know that would be an issue. My apologies. 1 minute. All right, 30 seconds. All right, I'm gonna lock answers here in 10 seconds. Locking answers here in 5, 4, 3, 2, and 1. Locking answers now. Shrink my faces, unmute y'all up here. So to get the gradient field, I got to find the what of this function f. Well, the gradient, which is composed of partial derivatives. So what's the derivative of that function f with respect to x? YZ. What's the derivative with respect to y? What's the derivative with respect to z? There's your gradient field. Any questions? All right. So we had just kind of a nice little thing. So we talked about vector fields. So vector fields are saying whether you're in 2D or 3D, you have a point in the plane and also direction and magnitude that you're heading in said direction. And one of the things that we like to consider with this is gradient fields, essentially vector fields that are gradients of some potential function f. Okay. So we're going to continue on today with a nice little theorem. So right here, yeah. Whoops, I'm not writing. There we go. Now I'm writing. So we're going to let f be a gradient field or a conservative vector field. On an open and connected domain. Essentially, open means it doesn't contain any of its boundary points. And connected just means that I can't break it up into two disjoint open sets. And we're going to let f and g be functions. Such that the gradient of f and the gradient of g both form that same vector field. If that's the case, then I can say something pretty important about those functions f and g. I'm going to get y'all to deduce what the connection is right now. If the derivatives of two functions are the same, that means the original functions only differ by a what? By a constant. So if these two functions generate the same vector field, that means these two functions only differ by a constant. Then there exists a constant c on the reals. So that function f is just the function g plus some constant c. So if you find one potential function, you find all potential functions. And another theorem with this, and more importantly, this is a way to tell whether or not you do have a conservative vector field. And it's a way to do it without trying to find the antiderivative, because up until now, conservative vector field, just a vector field that has a potential function. So I can figure out some function that I take the gradient of that function to get this vector field. Which means if I'm given a vector field and I want to try to find the potential function, I would have to integrate. And I don't want to integrate if I don't know if there is or is not such a potential function, because there could potentially be vector fields that you get that don't have potential functions. Well, there's a nice little easy way to check. So if we have a vector field f which in the x components is determined by a function p, and the y component is determined by a function q. If this is a conservative vector field, then the partial of that x component function p with respect to y has to be equal to the partial of the y component q with respect to x. If this is going to be a conservative vector field, then these two partials have to be equal. How the x variable changes, the x coordinate or x component of the vector changes with respect to y has to be the same thing as how the y component changes with respect to x. Now, if I go to 3 dimensions, it's going to be a similar statement. Oops. So if this is a conservative vector field, then not only do I have that the partial of the x component with respect to y needs to be equal to the partial of component y with respect to x, but it also has to be with respect to z. Let me move that over some. So when I do this comparison between the x component and the z component, these mixed partials have to be the same. And then also if I compare the y and z. There's actually a pretty easy proof to this. And we'll just do it in 2 dimensions because the idea expands up to 3 dimensions pretty simply. So we get to assume that this vector field f, which is a component of a function p and a function q, is a conservative vector field. Am I spelling conservative right? Yeah. If it's a conservative vector field, then I know there exists a what such that the what is equal to this vector field. If it is a conservative vector field, I can find a blank such that the blank of that blank is equal to the vector field. And partial derivative, what was that, Nikai? Same thing. What does it mean to be a gradient field or a conservative vector field? There exists a scalar function f such that the gradient of the said function is equal to the vector field. So since we've called this thing a conservative vector field, then there exists a function f Whoops, haven't used that notation in a while. Let me not use it. But how do I build the gradient of f? It's a vector. Its first component is built from what? What was the mumble? Partial with respect to x. And what's the second component made of? Partial with respect to y. Which means if those two things are equal, then how we also represent that vector field f is as a function p into function q. So what does this imply? Well, that then my partial with respect to x is just what function? And that function p. My partial with respect to y is just that function q. So then if I want to take the partial of this function p with respect to y, what do I get? Well, this is the same thing as a partial derivative with respect to y of what partial derivative? F of x. Which we just denote x, y, y, x. It doesn't really matter. Oops, you see an image below. You can ignore that image for a moment. But then if I take the partial with respect to x of the function q, really that's just taking the partial with respect to x of the partial with respect to y of the function f. And what do we remember about mixed partials? It didn't matter what order we did it in. Take the partial with respect to x and then partial with respect to y is the same thing as taking the partial with respect to y and then the partial with respect to x, thanks to something called a theorem by Clairaut. Well, let me get this out of here first. Clairaut's theorem, it doesn't matter which way I do those partial derivatives, they're going to come out to be the same answer. But that partial derivative is the partial of p with respect to y, the partial of q with respect to x. So there's our entire proof. If it's a conservative vector field, I can guarantee you, thanks to Clairaut's theorem, that the mixed partial, so partial of the x component of my vector field with respect to y, it's got to be equal to the partial of the y component of my vector field with respect to x. But this actually gives me a good test. I'm going to ask you to tell me what is the contrapositive of this theorem. What is the contrapositive of this theorem? So in short, this theorem says if my vector field is conservative, whoops, that's a weird X, then I have this relationship between my partial derivatives. Who remembers how to form a contrapositive statement of an if-then? Should have learned it in discrete. So it's you flip your hypothesis and conclusion and negate them. And that's what it means contrapositive. And contrapositive is always logically equivalent to the original statement. So once you get into some proof writing, let's see, no, you haven't taken intermediate calc 1, or not intermediate calc, you wouldn't have taken analysis 1 yet. And I think Adam usually teaches that. So it's your first big proof writing class, and you probably haven't taken abstract because I didn't see any of y'all in the fall. So contrapositive just says if I look at the partial with respect to y of the x component, and it's not equal to the partial with respect to x of the y component, then my vector field yes, but I'm just going to say not conservative. So now I have a way to test. If I want to determine whether or not a vector field is conservative, I take the partial with respect to y of the x component, look at the partial with respect to x of the y component. If they're the same thing, this thing is conservative, and I know I can find a potential function. If that's not the case, then there will be no potential function. Okay. So you get this nice little matching that you can do. But really, it's not a big expansion on any calculus concepts that we've been doing, just an application of them. What questions do you got for me before I move on to the next topic I want to cover? All right. Yeah, go for it. So for a vector field to be conservative, yes. You find take that component. So P is usually the X component. Take the partial with respect to a different component's variable. Make sure it's equal to that other component, your Y component. It's partial with respect to the first component's variable. Check. Yeah. If they're not equal, it's not conservative. If they are equal, it might be conservative.
So the function P can be different from the function.
Oh, absolutely. Mhm. Right. I guess we could say from the daily quiz. Oh, I'm afraid that I just turned off my phone. So the vector field that we got from Today's daily quiz was this. I have each component. The x component was what function? YZ. The y component was what? XZ. And my z component is XY. If I take the partial with respect to y of the function p, what is that going to be? Just z. Whoops. Py is equal to z. And then if I take the y component and take its partial with respect to x, what is that going to be? Let's see as well. So that pair matches up. But if I'm doing 3 dimensions, I got to do all pairs. So then I look at, okay, p with respect to the z components. So the derivative of the function p with respect to z is what? Y. And then I look at the rth component, the z component of my vector field. Take its derivative with respect to the variable for the first component, x. And then do qz and ry. What is the partial with respect to z of the function q? The x. What is the partial of the function r with respect to y? X. And all 3 of those pairs matched up because this is a conservative vector field. We generated this vector field from what potential function? F was x, y, z. X component, compare it to all other components, y and z. Take the y component, compare it to all other components, x and z. Take the z component, compare it to all other components, x and y. That's all there is to it. Mix and matching. All right, any other questions? All right, so then whether or not we're working over a vector field or just a nice little standard domain in R2 or R3, one thing of interest is something called scalar line integrals. So before, we'll just stick with 2 dimensions. Just try to make nice little more simple ideas. So far, when we've talked about integration, it's over an entire region. So something like this. We would integrate over that region D. With respect to A. Let me write on the left-hand side. We said, okay, well then I'm integrating over this range of X values and I'm varying between these Y values, and we learned how to set up those integrations and solve it. Well, this domain right here has how many dimensions? 2. A question, and I know this appears in physics, we'll see it in some of the like divergence theorems, Green's theorem, and a couple other things. But you don't always necessarily want to be integrating over an area. You might want to be integrating along a certain line or a certain path that you can be traveling in said domain D or just in R2. And some of y'all in modern physics right now might be able to come up with a good example. But instead, let's say I have a curve. In the XY plane. Every point along that curve has an X coordinate and a Y coordinate. And what I'm going to want to do is integrate my function along that curve instead. Now, how many dimensions does a curve have or a line have? Just 1. So I'm not doing my integration like I did before over a region, right? I'm not ranging between X and Y values. I'm ranging in a single dimension, and that single dimension is determined by the curve. So when I do integrations over a curve instead, well, it's just going to be a single integration for whatever my function is. We're going to see we're going to do a ds, and ds is just for arc length of the curve. We're going to break this down. How are we going to do this? See all my images that I want to keep for later. Let's see if I can keep them on the same page. Okay. So think back to how we built our Riemann sums, which gave us our integration. We took a region D, and let's even make it maybe just a little bit more simple for the sake of this argument. Instead of it being a type 1, let's make it a nice simple box. How did we go about approximating the volume underneath the curve over this region? We broke up the domain into small what shapes? Squares, rectangles, can be any. Squares makes it a little bit, it's rectangles, I think it's preferred because you don't want necessarily your change in your Y direction to have to be the same thing as your change in X. You get volume. You take 2 dimensions and raise it up. But now you have 3-dimensional shape. Right, the issue is when I was going from 3 dimensions and integrating with respect to a function, I was going to 4 dimensions. We didn't have the great language, right? So I took this domain D and broke it up into however many pieces I needed. I chose a point in each one of those domains to determine the height of these little rectangular prisms, and I added them all together to get an approximate volume. If I wanted to make it even more and more accurate, I would take those rectangles and make them what and what? Smaller and smaller. But okay, that's in 2 dimensions. If I'm integrating over a curve, my integration is happening in how many dimensions? 1. Well, think back to how we did integration of a function in a single dimension, but we just did it along the x-axis instead of a curve. I went from between the points A and B, And I broke it up into however many partitions that I want. But each of them were spaced evenly. And then based on that spacing, I had my function. Let me use a different color. Let's say it looked like that. I'd pick a particular point to then get my rectangles, height, and then use that to then get an approximation underneath the curve. Well, we took a single dimensional object, broke it up into little pieces, took a point from inside that interval to then determine the height. The same concept is going to happen here when we go to a curve. And it's the same concept that we did in 2 dimensions. Break it up into small partitions, figure out where along those partitions I want to take a point so that I can plug it into my function and get a height that will be approximate. And when I do this over a curve, I just have to be a little bit more careful because I don't get a straight line. And that's where this image finally comes into play that you saw me keep moving down over and over again. I'll copy and then delete that one. So we're going to take a curve. We're going to break it up into small pieces, small segments of said curve. We're going to write all this out. We're going to keep that image to the side for us while we do it. Okay. We're going to let C be a smooth curve. Oops. With the parameterization, sorry. So essentially, I can view the X and Y variables as functions of another independent variable, and that independent variable is shared between them. And that independent variable is going to range between an A and a B. So a common thing, and we like to do this even in diffq, T goes B's time. So as you travel through time, how your X and Y values are changing. Okay. So once you have that, we're going to partition that interval in time, my variable T, into little n subintervals. That's that Sn that we see up there. So this independent variable, I partition it up just like what we were doing before, even with single dimensions on the x-axis. It's now on the t-axis. And then in each one of those subintervals, we're going to pick a particular point. Point pi along that curve. And those points are going to be coming up for every point where I break up this partition of my independent variable. So that's where I'm getting this point P0, P1, and I have a P2, P3, and then I have a all the way through Pi minus 1, Pi plus 1, and keep going all the way to the very end. So I'm breaking up that t-axis into n equal lengths. That's going to give me n points, technically n plus 1 points. But what about the distance between those points? Are they always going to be the same? The answer will be no, not unless this is a straight line. If there are curves, distance between here and here, say, I think they give a good example right here from the textbook. Just visually, this distance between these 2 points along my curve is less than the distance between those 2 points on the curve. So I get this odd behavior of that where I break up my partitions, even though I break it up on the t-axis equally. When I look along my curve, the spacing along the curve between the points isn't always going to be the same. It's going to vary. And that varying creates a little bit of difficulty, but it's one that we can handle. So we're still getting n partitions, and we still got this idea of change in the length of the curve, but it's not going to be as simple. And when it comes to the actual calculation, but conceptually, I now have a way to get the Riemann sum. I take a partition along that curve. So something like from P0 to P1, I'm going to take a value from along that curve. I'm going to plug it into my function f, and that's going to represent my height. So now I have a width along the curve. I'm going to generate a height, which means I make a rectangle. And then with that rectangle, it has an associated what? I have width and height. Inside that rectangle is area. So I get an approximate idea of what the area is along this line underneath that curve. I just do that again over and over and over. And I just add up all of these different partitions. And if I do this to infinity, the integration over that curve C for this function with respect to the curve just becomes the length of each of those partitions along the curve, those delta S's, times the height, where the height's just coming from some particular point. So when I'm integrating over 2 dimensions with respect to a curve, I give it a height. The overall dimension of the shape we said is going to be how many? I'm integrating over a single dimension and I add height, which is another dimension, makes it 2 dimensions. So I'm essentially saying tracing along the ground some weird shape, and then I add height to it, which means I'm going to get some weird sheath. So you're going to have a piece of paper is a way to think of it, and that piece of paper is going to be wavy. It's like a ribbon hanging down. So, okay, cool. I get conceptually how to do it, but how is this going to help me actually calculate? Well, we have all the pieces that we need, specifically something like the parameterization. Now, this curve changes with respect to x and y, But because I can parameterize this curve with respect to a single variable t, that means I can probably turn this integration over a curve into integration with respect to the variable t. And I know that the variable t is only going to be between a specific value a and a specific value b. Which means at the end, it just comes down to a nice little simple one-dimensional integration. The question is, how do I set it up? So I make sure that I'm accounting for all these different varying lengths in S, and also this general curve C. So, oh wait, hold on. I took it out, and that's why I was like, wait, I feel like I'm missing something. So this is the image I'm trying to get you to replicate in your heads. So I have a curve C, which I can see right here. It's a nice little like U-type shape, and you can see it more projected up here. Again, nice little curve C in the XY plane, and I'm integrating with respect to this function f of xy, which is creating this sheet in 3 dimensions. Right, it has X component, Y component, and Z component. If I'm integrating with respect to this curve C, I'm trying to figure out what is the area underneath this function f of x comma y along this curve. So I'm just creating a single sheet. You can see it right here, a single sheet that follows along. If I did this over 3 dimensions, I'd be creating volume if I'm integrating over a curve, which is what usually you use in physics. So you can stick within 3 dimensions. I remember my calculus-based physics correctly. That was over a decade ago, so that's could be off. But this was the image I kept trying to say. When I say sheet, this is what I'm talking about. So I guess before we actually oh crap, I have 2 minutes. I probably won't be able to get through that page. So now we're gonna have to just settle with this is setting it all up. So when's the next time we meet for intermediate? Yeah, Monday. So on Monday, what we'll do is we'll start answering that question. How do we actually do this evaluation? With respect to Riemann sums, I know how to get it, but we never want to ever do direct calculation from Riemann sums. We want to use all the stuff that you built in calculus 2, all of your integration rules instead. So if you got questions for me, now's the perfect time to ask them. Otherwise, feel free to actually have a 10-minute break before defeat. Yeah. Where I find it. So let me stop the recording so I can start processing.